Hello everyone. We will start our talk, then people will join later. So today we are going to talk about various equilibrium conditions in classical mechanics. So basically we are talking about stable and unstable equilibrium. And this is the topic in classical mechanics which generally have one to or two questions every year on GATE examinations. So we will start this talk with the conditions of this kind of mechanism. Basically, it's a system in which you can use to solve various problems in classical mechanics, but it is valid only for conservative forces. So always remember that whenever you try to find this condition of stable and unstable equilibrium, you are basically talking about conservative forces for which there is no non-conservative force, like there is no friction or any other forces in this kind of system. So our total energy, which is the sum of kinetic energy and potential energy, it is going to be constant in this system. So from this equation, this says that your kinetic energy and potential energy of your system is going to be constant. Then you can just take E as some constant. And from there, you can just take a velocity factor outside and just manipulate these things. You will get dx by dt. I have written velocity as dx by dt. So this term is just, I just take E minus U on this side and multiply 2 by m. Since this is v square, so v become this quantity. And when you differentiate this quantity, your dx will become a function of dt. That means if you integrate it, your x will become a function of t. So this will give you trajectory or motion of your particle. Like at time t equals to 0, t0, your particle will be at some other position which you say as x naught, and at time t equals to t1, it will be at some other position x1. So you can say if you know how your x is vary as a function of time t, you can say how the motion of your particle is there. So just by integrating this, you will get the trajectory of your particle in the system. And if you look at this expression, your energy is constant. So just integration factor is kind of dependent on your potential energy. So if you change your potential energies, for example, in case of harmonic oscillation, you know that your potential energy has a kind of parabola, something like this. If you plot u as a function of x, that means yes, someone is raised hand.
Ma'am, what if there is a non-conservative force?
For non-conservative forces, this kind of position equilibrium condition is not valid. Means then you have to use some other formalism like the
Ma'am,
one you
what
use
is the
in
reason?
what? Can you repeat?
What is the reason? Means, why do we need conservative forces for this
For this thing?
stable
Actually,
or unstable equilibrium?
actually, this is a kind of conditions we use to solve problems in classical mechanics. But this kind of equilibrium condition is not possible if you have some kind of drag in your, like you have some friction. So your motion is not going to be equilibrium. It will be like dying. For example, if you look at the trajectory of your particle, it's kind of moving, but its energy is kind of decaying exponentially and eventually it become rest. So equilibrium means you have some position around which you perturb it little bit and it start oscillating about this position equilibrium. Or you have some condition in which the particle you perturb slightly and it just move away from the position. But in case of non-conservative forces, your particle eventually may be stopped. So this kind of condition we are not using here. We are using the condition that your particle is not stopping because of external influence. It's kind of going to move even after slight perturbation. So that is mean by equilibrium. A certain conditions which required. for a particle to be at a position, not
Okay,
because
ma'am.
of,
Thank you.
okay. So we are talking that if your position x is a function of time t, you can say what is the trajectory of your particle. And since this formula will contain the potential energy, so different type of potential will give you different type of trajectory. For example, in case of harmonic oscillations, you have particle oscillations around certain positions. So your potential is like parabola. So your particle is moving around this equilibrium position. But if you have a gravitational kind of potential, in that case, you know your particle is moving in certain elliptical kind of trajectory. So different potential will lead to different trajectories. So we are not going to talk about whole system here. We are just focused on potential energy part to describe the various conditions. And this will give you a kind of qualitative way to understand what is the particle trajectory, and it will not give you quantitative answer here. You just can simply say that this can't be the motion of particle, but you cannot actually give the value of the velocity of particle using this kind of formalism. For that, you have to again go back to your either Lagrangian or Hamiltonian mechanics or Newtonian mechanics. Okay, so I think you are all familiar with this kind of simple example. Someone want to say something?
Ma'am, please repeat again.
Repeat the last one part.
Yes, ma'am.
Okay, actually we are talking about the conservative systems in which our total energy is conserved. And from that total energy part, we say that our x is going to be a function of time t, and we derive this formula from which we can say that at different times we have different trajectory of particles, and that trajectory of particle is dependent on your potential energy. So we are talking mostly about the potential energy part in case of energy to describe how the motion is going to behave, and this will give you a qualitative understanding of this thing. It will not give you the actual number, what is the velocity and all other thing. It just give you how the particle is going to behave. So this is kind of simplest way to solve gate questions. So for example, if you have considered this kind of situation in which you have a ball and you throw upward, then you say that the potential energy is given by mgy at certain position y, but at a complete height h, it will be mgh, and at that position it will become rest, and then it come down again. So at that position, your kinetic energy will come zero, and you have only potential energy. So your total energy will become equals to your potential energy. And in between position like Y, you have both kinetic energy and potential. Initially, you have kinetic. So eventually, your total energy, since your kinetic energy is always a positive number, so your total energy always have to be greater than potential energy. And this must be important for any kind of motion. For example, if you look at this formula here, you have square root of E minus U with some constant. So if your energy has to be greater than U, so that inside this square root you have a positive value. If you have negative value here, in that case your potential energy become greater than total energy, then this will become imaginary motion that will not be possible in any real case. So this condition has to be valid that your total energy should be greater than your potential energy for any kind of real motion. For example, let us consider this case of potential energy where you have some random potential curve. For example, in case of harmonic potential, you have parabola, but here it is some different curve. You have different conditions of energy, like E1 is the energy level, E2, E3, E4, and some E0 as well. So you have to find out how the particle is going to behave at these positions. And to calculate that, we will use, and you already know that your energy has to be greater than potential energy. So if your energy is E0, then your particle is going to behave only at this position. It will not go on this side or on this side, because in that condition your total and your potential become greater than your total. For example, if you look at E1 case, this is your total energy. This regime correspond to your potential energy U is less than your total energy. This is valid, but if you look at this case, here your potential energy become greater than E. So your motion is not possible in this case. So your particle will go there and then once its energy is reached, it come back on this side. So it will kind of start oscillating in this regime. And this is because of this condition for the particle that your total energy is greater than potential energy. And we have to find out how it is going to behave in other energy level like this one too. And for that, we will have to find what is the equilibrium. So I think you have already learned this condition of equilibrium in Newtonian mechanics. When if you have some block and you apply some force F1, then it will start moving in this direction. And if you apply equal and opposite force in other direction, then the particle will become rest. And this position is known as equilibrium in Newtonian mechanics. And as someone asked for the case of non-conservative forces, in that case you can consider friction force here in Newtonian mechanics. But we are not talking about Newtonian mechanics here. So we are talking mostly about the energy levels. So in this energy case, we are not talking about frictions. We are mostly talking about conservative forces. So in equilibrium condition, your force has to be zero. And for conservative system, we can always write our force as negative gradient of our potential energy. This means this term has to be zero for equilibrium. So the necessary condition for a system to be in equilibrium is that your gradient of potential energy is zero. And if we are considering one dimensional case, then it will be del by del x. And that point, which is come out after putting del u by del x equals to zero, that condition x0 is known as the equilibrium point. We will solve some problem that we will find how to calculate this point in certain conditions. And since we have plot this u versus x initially, this is u versus x. So you already know that if you have equations of line, something like this, then your slope is given by del v by del x, and therefore in that case del u by del x will represent the slope of this line, and we want our slope to be zero at the position of equilibrium. So if you look at this plot, whenever you have this flat position, this will correspond to equilibrium points in your u versus x plot. So if you are able to draw u versus x plot in your diagram, then you can just by looking at this flat point, you can say that these are the equilibrium points. And whether it is stable or unstable or neutral, that we will see. For the stable equilibrium point, the condition is if you perturb it slightly, then it will come back to this position, even slight perturbation, and that will correspond to stable equilibrium. And if it is unstable equilibrium, then if you perturbed it slightly, it will just roll away. It will not come back to this position again. And that will correspond to unstable equilibrium. And neutral is generally possible only for case of, you know, horizontal flat surface. You just place this particle here and it will stay. Neither it come back to this position nor it just move away further. It just stay as it is at this perturbed position. And that will correspond to neutral equilibrium. And I think this kind of condition is possible for non-conservative type of forces where your energy of particle is kind of just finish up so that it will become at rest at this position. So this kind of condition is possible for non-conservative type of forces. So whenever we try to find the formula in terms of potential energy about this stable and unstable equilibrium, what we do is we just do the Taylor series expansion of our energy at the about the equilibrium position. So this is your potential energy, and you just do Taylor series expansion. I think you have known that if you have a function f and you wanted to do its Taylor series expansion about any point x equals to a, you just write f of a plus first derivative f dash a into x minus a, and then second 1 by 2 factorial, second derivative, and x minus a square. So this is the Taylor series expansion of your potential energy with respect to equilibrium position. So the first term ux naught is some constant. You can put it 0 as well. The second term is 0 because of equilibrium condition. Your del u by del x has to be 0. And now this is the third condition, third term in this Taylor series expansion. And yeah, someone raised hands. And
मैम हम इक्विलिब्रियम पॉइंट को क्यों कैलकुलेट कर रहे हैं?
basically today's lecture is about the conditions of equilibrium and non-equilibrium for a classical system. So just by looking at your
मैम
potential,
जैसे
you wanted to calculate.
मैम लैटिस में भी तो
Yes.
वाइब्रेशन होता है ना, तो उसमें भी हम इक्विलिब्रियम पॉइंट निकालते हैं क्या? मतलब क्या उसमें
Uh,
इक्विलिब्रियम पॉइंट क्या बताता है लैटिस में?
and that one is different case, but it is the extension of this lecture. Means I haven't included today's talk, but yeah, in that case we also calculate our equilibrium position. I think you are talking about that system in which about this spring and you have an atom and you just displace it little and it come back to its
यस
position.
यस यस यस
That condition is also valid here, but this requires little complete lecture. We will cover in next class because there are certain questions that are appear in GATE exam on this topic alone.
ओके
Okay,
कंटिन्यू मैम.
okay. So if you write your potential energy as a function, then these three terms out of these two terms, and this is the third term. And now if you look at your third term, it is very similar to like spring potential, the one we have discussed right now. In case of spring, your potential energy is given by 1 by 2 kx square with k as a spring constant, something like this. So your k as a spring constant. And in that case, your potential energy here is also represent like this. With k, which is the spring constant, is given by del u by del x square. So if just by looking at this spring constant, we can say is it a stable equilibrium or unstable equilibrium. So the sign of this function del u by del x square at equilibrium point, if it is greater than 0, that means it will represent a parabola something like this, and this will correspond to a minimum condition, and this will means a stable equilibrium. However, if your k is less than 0, that means you are at the top of this flip parabola, and that will correspond to unstable equilibrium condition. So if you look at this plot again, if you are at this position here, then you can not move on this side or on this side because your total energy is the minimal, and your potential energy is always going to be higher than this. That means with this constant energy not you only can do circular motion. And if you have a little higher energy even in that case, if you slightly perturb your particle, it will move on this side, and since your total energy is just this much, it will go back to on this side. So this is the potential energy and this is here your total energy. So you have left some kinetic energy at this position. With that, you just move back. So it will start oscillating in this region. So if your total energy is even, then you start doing oscillation, and this will be a stable equilibrium point since it is like this in UX curve. And if you have E2, then there are two stable equilibrium, one at this position x naught, and since energy E2 is here, so you have another position which is here. So with E2 you have again oscillation, but this time you have two stable equilibrium. If your energy is E3, then you have one unstable equilibrium, another one here, but this one is not possible. This is possible only for E4. So you have to see what is your total energy and what is your potential energy curve is showing you. That will help a lot if when you are doing a gate problem. They are very straightforward and very easy to calculate in exam. For example, this is the type of question you will. Yes, someone raise hand. Is it previous one? Okay, I think this one is previous one. So this question, this type of question you will encounter in your GATE exam, in which a particle is moved in x greater than 0 regime and the potential is given by this kind of form. So find an equilibrium point and check their stability as well. So if you try to plot potential energy U versus x plot, what you do is you just plot each and every term one by one. For example, this first term, you you just take u naught on this side. It is a constant. So you are left with a by x. So if you look at this term, it is like 1 by x kind of plot. So this is how inverse 1 by x plot is going to happen. So this is your a by x term. And if you look at this term, you by u naught as x by a, the second term, that means it is proportional to your x. So this is y equals to x kind of graph. And the point where they meet, it just kind of change its position. So this is your final graph for u versus x. And as you can see, there is an equilibrium point where this become flat. And you have to check.
मैम
Yes,
एक्स की दो वैल्यू मिलेगी ना एक्स इक्वल टू प्लस माइनस है
that we will see. If we will get two values, then either there will be, that we will see. X square, yes, there are two values, plus minus a. Then we have to check our stable and unstable equilibrium. So you are given ux, and for equilibrium, you just take del u by del x is 0. And from there, if you calculate, you are left with x square equals to a square and x is plus minus a. This is your equilibrium point. And if you check its stability, then at x is equals to plus a, you will get a stable equilibrium. And x equals to minus a, you will get 2u naught a by minus aq. So that will be negative, and that will correspond to unstable equilibrium. So there should be an unstable equilibrium as well. I don't know where this one lies.
No, ma'am, there will be only one equilibrium because in the question it is given A should be greater than 0. So A should be positive.
Oh, sorry. Yeah, that's one. Thanks. So a should be greater than 0. So there should not be any negative one case. Thank you. So we will just have one stability point. And there are several gate questions that
मैम मैम
yes.
यदि यहाँ पे ये कंडीशन नहीं देता ए ग्रेटर देन जीरो की तब
Then you have to plot for, you have to extend your plot in negative direction of x by a, similarly minus a by x. and then you have to see how your plots is vary.
मैम इसका जो डबल
Then
डेरिवेटिव करते हैं, अगर वो हमें पॉजिटिव मिलता है तो वो स्टेबल होगा, राइट?
yes, if it is greater than zero, then it will be stable. And it's not for potential, but it is, I think you have learned in your 12th class also when you
यस
read
यस यस।
maximum minima chapter that if you have some function del 2y by del x square, it is greater than zero, that will correspond to minima condition, and that is a stable equilibrium. So all those formulas are valid here.
ओके।
Okay. So we will solve some gate questions. For example, a particle is placed in a resin where potential is given by this. Then we have to find what are the equilibrium points and is it stable or unstable. So we are given a potential like this, and we have just calculate the equilibrium position by putting del V by del x equals to 0. From there, we will obtain 2 points x equals to 0 and x equals to k by lambda. So when we differentiate it with respect to x square, and we just put it for two values. For x equals to 0, we will get k only. This term becomes 0. So it will be a stable equilibrium. And for k by lambda, this term will become negative. So that will correspond to unstable. So for k by lambda, this is the point of unstable, and for x equals to 0 is a stable equilibrium point. So this was the question from GATE 2010. And this was from GATE 2012. A particle of unit mass move along x-axis under the influence of a potential given by this formula. The particle is found to be in stable equilibrium at x equals to 2. Find the time period of oscillation of particle. This point I haven't covered, but if you have a stable equilibrium point, you know that the particle is going to oscillate in between these two resins. So there will be a time period of oscillation. So if you know that for a case of spring, whenever your potential is given by Vx equals to kx square, you just calculate their force which is given by del V by del x kx, and del 2v by del x square will give you k. So your angular frequency of oscillation is given by square root of k by 1. This is known in case of spring potential. And from there we will calculate the time period of oscillation. So this we are going to use here too. We know our potential. We calculate the equilibrium condition del V by del x equals to 0. So we get 2 points, and it is given to us that at x equals to 0 we get a stable equilibrium. So at equals to, we just calculate del 2v by del x square, and at x equals to 2 we get a stable equilibrium. At 2 by 3 although unstable, we just check it. So we calculate del 2v by del x square at x equals to 2, which is 4, and it is given to us mass is unit mass. So we just put m equals to 1. So your angular frequency of oscillation is square root of 4. And from there, time period of oscillation is comes out to be pi. I think you all know that angular frequency is given by 2 pi by t. So t will become, so this is the time period of oscillation. And the same kind of question was appeared in GATE 2014. A particle of mass m is given by the potential. So the form is potentially changed, where a and r0 are positive constant. So they are greater than 0. When disturbed slightly from its stable equilibrium position, it undergoes simple harmonic oscillation. What is the time period of oscillation? Again, you are given a potential. You calculate the equilibrium condition. Now the potential is a function of r. So you have to differentiate with respect to r. You just put it equals to 0. So you have two values of r plus minus 0, and it is given to us that they are the positive constant. So we do not have to check it for minus r0, even though it gives unstable equilibrium. So it is given to us that r has to be positive. So we calculate del 2v by del r square, put r equals to r naught, the positive value, and we get a stable equilibrium. So what the time period of oscillation? We just calculate angular frequency at r equals to r naught, and this will give you your time period of oscillation 2 pi mr q pi a by 2a. This one's answer. And two questions was appeared in GATE 2020 exam. So the first one is a particle is moving in a central force. Okay, this one is different in the sense we are not asking for conditions of equilibrium, but we are given that. Yes, someone asking. Okay, a particle is moving in a central force with r cap as a unit vector pointing away from the center of the field. The potential energy of the particle is. So the one thing that you have to see in this question is particle is moving in central force field, and these forces are conservative in nature that we have covered in last classes. That whenever you have central forces, we are always talking about conservative forces. And whenever you are talking about conservative forces, you can always write your force as negative gradient of potential energy. So your force is negative gradient of potential energy. You just integrate it with respect to R, and you will get your potential energy, which is minus k by 2r square with some constant. You can find this constant by condition that as r tending to infinity, your potential energy will become zero, since this term will going to dominate. So from that you can find that C is going to be zero. So this will give you the potential energy. And that was question from GATE 2020 itself. The potential energy of a particle of mass m is given. This time this is a sinusoidal kind of form. What is the angular frequency of a small oscillation of the particle about x equals to 0? So ux is given as this form with a greater than 0 and k square greater than 0. So you can all, I think you all know that if whenever you have sine of something like pi by 2 minus x, you can always write it as cos of x. This is the quadrature change. So here the minus pi by 2 on this side. So if you take minus outside, this is the kind of ux will write. And just you do the expansion. Some same like we have done for the potential energy around equilibrium point. So try to do the questions, this kind of question or some exponential by doing the expansion. It will make your life easy. So try to limit to three terms. One is correspond to u at x naught, another first derivative, and then this one correspond to second one. So when you do del u by del x, this term will become zero, only this term left, and this is also there. And from there you are left with x equals to 0. And when you do del u by del x square at x equals to 0, this is the only term survive. And we have to find angular frequency. So omega Lx at x equals to 0 is given by this term divided by n. So it will become k square root of a by. And that's the same concept apply in this question from GATE 22 exam. A particle of unit mass move in a potential. Here the potential have some exponential form.
Excuse me,
So
Miss.
you know, yes,
Miss, in the previous question, we were given, we were asked to find the uh, same solution for x equal to a instead of x equal to 0. Then would we need to rewrite the potential in terms of x minus a?
can you repeat? X minus
Uh,
a means?
I mean, the potential which is given, it's sine k square x minus pi by 2. Would we need to rewrite the potential in terms of sine k square x minus a? So plus minus a, we would we be required to do something like that? Had we been
No, we
given
do
that?
not have. No, we do not have to do that thing like. We calculate the equilibrium position and then we have to put that value again on our potential. This kind of thing is not necessary for that. You just calculate
मैम
your derivative. Yes,
जो ये फ्रीक्वेंसी हम निकाल रहे हैं वो स्टेबल पॉइंट के अबाउट ही निकाली जाएगी ना?
yes. For
या
unstable point, there is no oscillation, so there is no frequency.
या ओके.
Okay. I think I have answered several question as well. We do not have to write our potential again by putting all those values back into our potential formula.
Okay.
Okay. So for example, in this question, we have given the potential in exponential form, e to the power minus r square. And you know that if you have e to the power minus x, you can expand it like 1 minus x plus x square by 2 factorial. So we are going to do that thing here. If the angular momentum of particle is given, then which of the following statements are true? So the question is, it is understanding particle is moving under a potential, which is just a function of coordinate system, and its angular momentum is constant. If you look at L equals to 0.5 square root of V naught, V naught is constant here, zero point 0.5 is also constant. So your angular momentum is constant. Your V is a function of R. Both these conditions will correspond you to the central forces. So in that case, you have to use effective potential instead of simple potential V. So in forces, if you want to see the condition of equilibrium, you have to use effective potential, which is the sum of your potential energy plus L square by 2mr square. And because your total energy is given by kinetic energy plus free effective potential energy in case of central forces. So we write our effective potential, which is the sum of potential plus L square by 2mr square. If you write L square, this term will become 0.25 P naught, which is like 8 r square m I have taken 1, 8 multiplied by 1. And just expand this term also. So your V effective will become this one. You just differentiate it with respect to r, put it equals to 0. Then you have left with r square and r to the power 4. From there, you calculate the value of r. I'm just taking two values. So your r, this term is your r square, and from there you calculate your r. I have removed all the negative values here since r
मैम
can
आपने
take
एम
by
ही
a positive. Yes, this m is not
मैम
mass.
आपने एम
This is strict, yes,
वाई
constant.
अच्छा यूनिट मास अच्छा अच्छा अच्छा
It's not
या
this at this place I have take unit mass, but this m is not for mass. It's just m equals to r square, some constant, just to solve this
यस मैम
equation.
क्वेश्चन में मेंशन है यूनिट मास यस क्लियर.
Yes. Okay, so you have R values. You calculate del to V by del R square. And for that, you, R equals to 0.92, you calculate your del to V by R square. It will turns out to be negative, so it's an unstable equilibrium. And for R equals to 0.38, you again calculate value. This is positive, so stable equilibrium. So you have 2 points. One is a stable equilibrium and another one is unstable. And they have given it in terms of R1 and R2. So you have to check stable at R1 and R1 is less than R2. So you have stable at R1 which is 0.38. So R1 and unstable at R2 which is 0.92. And it is given that R2 is given R1. So yes, this answer is correct. All other answer there are two equilibrium points along radial coordinate. There are yes, there are two equilibrium points along radial coordinate. This is also correct since your values are in terms of R. You do not have any theta coordinate here. So that's why you have only radial coordinate. So this is also correct. There are two unstable equilibrium points along radial. No, one is stable, another one is unstable. One equilibrium point. No, there are 2 points. Okay. So there are two correct options in this question. Okay, these are the questions that I have found from previous.
मैम मैम वन
Yes,
मिनट जैसे क्वेश्चन में मतलब मैं स्टेबल पॉइंट निकाल दिया मान लीजिए मैंने इसको ये एमसीक्यू टाइप क्वेश्चन है ठीक है तो इसमें मैंने
yes,
बी को ही टिक किया है आंसर में आप क्वेश्चन पे आइए एक बार
हाँ,
मैंने इसको बी पे ही टिक किया एम एमएसक्यू टाइप क्वेश्चन है ए को टिक नहीं किया तो मुझे इसके नंबर मिलेंगे क्या
nine. You will get zero. That thing happened in this
यदि मेरे
GATE
मान
exam.
लीजिए
That's why.
तीन ऑप्शन सही होते हैं इसमें मान लीजिए आप
Yes,
ठीक है तो तीनों ऑप्शन में से मैं दो ऑप्शन सही कर लेता हूँ और वन छोड़ देता हूँ मतलब मुझे उसके बारे में पता नहीं तब भी नंबर नहीं मिलेंगे
yes, you will get zero. Actually, that's why GATE become tough. Even though questions are easy, just because you are not able to identify all the correct option, you will get zero. So if you have spent your time in solving GATE question, try to go through all the options.
ओके
Otherwise, don't touch the question at all. You will spend more time solving other question that was is easy so that you can score better.
यस
Okay, so is there any other doubt?
तो मैं
Okay, you will score in this question on this topic in GATE exam eventually. This is not a tough.
Ma'am, ma'am,
Yes,
can you just show the plot you have shown earlier, like
for
the
this one.
yeah this one. So if we consider the energy is E2, so there are two regimes where the particle can stay, right? So
Yes,
if at t equals to 0, if the particle is in the first well, then
yes.
is there any probability that uh, at t equals to any time after that the particle can be found in the other well also?
With energy E0.
No, with energy E2.
With energy E2, you have the probability that you can find the particle on second well, but with energy E0, it is not possible.
So, ma'am, how can you justify the transition from one well to the other using classical mechanics? If we consider quantum tunneling, then it is fine. But using classical mechanics, how can you justify the transition from one well to another?
That I don't know. Generally, I think classical mechanics uh, cannot provide the answer. That's why there is a quantum mechanics. And the tunneling phenomena is only explained by wave functions. And here we are
Okay.
not talking about wave functions. We are just talking about energy.
Okay, ma'am.
Ma'am, how will it go in second well? Means it cannot have an energy which can cross that potential, no? The
So that's
unstable
why the
equilibrium
question
point.
is, that's the same question that is answered by Amit, that in quantum that is possible with tunneling phenomena, which says that your wave function has some decaying kind of form that will lead to this uh, transition. But in classical mechanics, we generally describe things in terms of energy, so we cannot. I don't know the answer till now, but we will. I can try to find if possible, but I don't know till yet. With classical mechanics, how can you explain this transition? Okay, so is there any other doubt?
Ma'am, I have one question from EMT.
Okay, so have you
Ma'am,
posted it on Telegram?
not posted. Uh, can I post it now?
Yeah, you can post it. I will see and try to formulate your answer and then send you the pic on Telegram again.
Okay, ma'am. 1 minute.
So if there is another topic that you people want me to cover in next lecture, you can tell me. I will cover in next class.
Ma'am, oscillation in next topic.
Okay, we will cover oscillation next class. Harish, I will answer your question on Telegram. Means I will solve your question and send you there.
Okay, ma'am. ग्रुप में शेयर करना है क्या इसको मैम?
Yes, you can share with group.
यस 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 हाँ मैम,
Yes.
नेक्स्ट क्लास में आप एक बार ईएमटी को ले सकते हो क्या?
Yeah, if you have any doubts, you can ask, and I will start my lecture with this solution, and then we will start.
मैम मैम देखो, आप ईएमटी में जैसे ईएम वेव होते हैं, जैसे तीनों तीनों मीडियम के लिए हो गई ईएम वेव, उसके बाद नॉर्मल एंड ऑब्लिक इंसिडेंट आता है, ठीक है?
Yes, yes.
उसके बाद मैम और क्या टॉपिक रह जाते हैं? जैसे लॉरेंज और
There is
बोल्स
this radiation,
ट्रांसफॉर्मेशन हो गया.
there is this radiation part, and then
यस यस
uh, Lorentz transformation of E and
यस
M
यस
field.
यस.
Yeah, that
तो
I
मैम ये
haven't
जो
covered.
यंग डी सिलेट एक्सपेरिमेंट है ना, ये कौन से टॉपिक से रिलेटेड है? जैसे ऑर्डिनरी वेव पढ़ते हैं ना प्रिज्म में,
Okay.
बाय प्रिज्म में.
Yeah, this one is a part of EM wave, but it is not taught in EMT explicitly. It's a part of optics.
बट मैम देयर आर सम क्वेश्चन फ्रॉम दैट टॉपिक इन द गेट
Yeah, this
एग्जामिनेशन.
part is optics separately. So we do not talk about EMT with this topic. Generally, EMT finish with electric and magnetic field, and the
मैम
intensity
जैसे
part is
जैसे
magnetic.
यंग यंग डी डी सिलेट एक्सपेरिमेंट है,
Yes.
तो वो तो मतलब ईएमटी में उसके तो क्वेश्चन आए हुए हैं.
Even there are questions from polarization and biprism. I don't know. Bifringent material is also there when you talk about ordinary and extraordinary waves.
यस यस.
So, these are, I think, two main topics from optics. One is double slit experiment, another is polarization.
यस. तो मैम उसमें पोलराइजेशन में पता क्या दिक्कत आ रही है? उसमें मतलब पोलराइजेशन कौन सी डायरेक्शन में हो रहा है उसको कैलकुलेट करना नहीं आ रहा है एक तो, ठीक है?
Circular or means clockwise or anti-clockwise.
क्लॉकवाइज, एंटी क्लॉकवाइज और इलिप्स और सर्कुलर. हाउ
Okay,
वी
I will
विल
cover
डिफाइन.
that topic in detail if you people want.
ओके. मैम आई हैव सम प्रॉब्लम रिलेटेड टू ईएम वेव. ओके.
Traveling
एंड
in,
like there are many problem from that topic. ओके. और मैम वन एक क्वेश्चन और है कि जैसे नॉर्मल और ऑब्लिक इंसिडेंट्स वाला टॉपिक है ना, उनमें से जो
hmm,
क्वेश्चन बन रहे हैं ना, वो क्वेश्चन नहीं मिल रहे हैं मुझे.
अच्छा, oblique and normal incidence wale.
नॉर्मल इंसिडेंट. हाँ हाँ हाँ.
I think you have that question in notes. In the last page of this note, there are several questions that are solved.
या
You can go through that if you can find some.
यस आई हैव दैट नोट्स मैम, यू ऑलरेडी शेयर्ड विद अस.
If you can find some, that will be good. Otherwise, you can just solve the last year problem. That is enough from that topic.
ओके मैम, तो मैम फिर नेक्स्ट सेशन में हम कौन सा टॉपिक लेकर चले?
Oscillation, and then
ऑक्सीलेशन।
we will cover that polarization part.
ओके, और मैम जैसे मेरे ईएमटी में मतलब कोई क्वेश्चन रहता है वो मैं आपको मतलब वहाँ शेयर कर दूँ तो मतलब
ग्रुप
आप
में शेयर कर
सॉल्यूशन।
दो, हाँ, ऐसे।
हाँ हाँ हाँ।
ओके।
यस यस, थैंक यू मैम, आज का सेशन बहुत ही हेल्पफुल रहा।
Okay, thanks. Next time we will cover for more. Bye bye.
बाय बाय मैम।